I keep hearing
Yep.
about this. That's one of the big breakthroughs in computers is going to be quantum computing.
Google built a quantum chip that did something physicists said was impossible. And the moment it proved them wrong, it vanished from the experiment entirely. No explosion, no failure. The chip worked perfectly. That is exactly what scared them. Because what Willow showed in those final test runs before Google went quiet was not just a breakthrough in computing, it was a result that broke the theoretical framework the entire field was built on. They got the answer. They could not explain how. And then, without announcement, the deepest part of the experiment disappeared. The machine. There is a machine sitting inside a Google lab in Santa Barbara that looks like something out of a science fiction film. It hangs from the ceiling on thin metal rods, encased in layers of gold-plated chambers, cooled to temperatures 15 times colder than outer space. It costs billions of dollars to build, requires a dedicated engineering team to maintain, and operates according to principles that the world's most brilliant physicists still argue about at conferences. Its name is a reference to a willow tree, something that bends without breaking, that finds stability through flexibility rather than rigidity. The choice of name turned out to be more apt than anyone realized at the time. It is called Willow. And in December 2024, it did something nobody expected. To understand why that matters, you need to understand what a quantum computer actually is. Because it is not what most people think. Your laptop processes information as a sequence of zeros and ones. Every calculation is a series of binary choices, yes or no, on or off, one state or the other. It is fast, but it is fundamentally limited to exploring one path at a time. A quantum computer operates on a different set of rules entirely. At the quantum level, particles do not behave the way objects in our everyday world do. They can exist in what physicists call superposition, meaning they occupy multiple states simultaneously until the moment they are measured. A quantum bit, or qubit, can be both 0 and 1 at the same time. And when you chain thousands of qubits together, the computational possibilities do not just multiply, they explode exponentially. Think of a classical computer as a single person trying to find the fastest route through a city. They pick one road, drive it, come back, try another. A quantum computer is as if you could split yourself into millions of versions simultaneously and try every possible route at exactly the same time, collapsing back into a single person only once you have already found the answer. That is the theoretical power of quantum computing. The problem, and this is a problem that has haunted the field for decades, is that qubits are extraordinarily fragile. The slightest vibration, the faintest electromagnetic interference, even the heat from a nearby object can introduce errors. This phenomenon is called decoherence, and it has been the central obstacle standing between quantum computing's theoretical promise and its practical reality. Every time you add more qubits to a quantum system, you introduce more potential for error, more noise, more chaos, more failure. The prevailing assumption across the entire field was that scaling quantum computers would always be a battle against this fundamental instability. More qubits meant more problems, not fewer. That assumption had held for 30 years. Willow broke it, and in breaking it, revealed something far more unsettling than anyone anticipated. Below threshold. The announcement arrived in December 2024 in the form of a research paper. Google's quantum AI team had achieved what the field calls below threshold error rates. In plain language, that means something genuinely strange. The more qubits they added to Willow, the fewer errors the system produced. Read that again. Adding more qubits made the system more stable, not less. This is the opposite of everything prior quantum computing research had suggested. It is the equivalent of discovering that adding more musicians to an orchestra does not produce more noise. It produces a sound so precisely coordinated that every individual imperfection cancels out into perfect harmony. The mechanism behind this breakthrough is called the surface code, a method of spreading quantum information across many physical qubits in a specific geometric pattern. Instead of storing a single piece of quantum data in one fragile qubit, the surface code distributes it across dozens or hundreds of qubits simultaneously. When an error occurs in one part of the system, the surface code can detect and correct it by measuring the relationships between surrounding qubits, without ever directly measuring the quantum data itself. That last part is critical. In quantum mechanics, measurement is destructive. The act of observing a quantum state collapses it from its superposition of possibilities into a single definite outcome. This is the principle behind Schrödinger's famous cat. The quantum system exists in all possible states until you look, and the act of looking forces it to choose one. For quantum computers, this means that trying to check for errors in the traditional way would destroy the very information you are trying to protect. The surface code gets around this by measuring indirectly. It looks at the environment surrounding the quantum data, not the data itself. The way you might infer that a car has driven through a puddle by looking at wet tire tracks without ever stopping the car. What Willow demonstrated was that this approach does not just work. It works better and better the more qubits you add. The system was bootstrapping its own reliability, becoming more coherent as it scaled, not less. And then the team noticed something else, something that did not make it into the official announcement. Disappeared. Here is what the headline got right. Willow, it disappeared. Here is what it got wrong, the timeline. It did not disappear after the announcement. It disappeared before anyone outside that lab knew what they were looking at. In the weeks before the December 2024 paper was published, Dr. Hartmut Nevin and his team at Google Quantum AI were running extended experimental protocols that went well beyond the benchmark results. They were pushing Willow into territory that had no established theoretical framework, asking the chip to solve problem sets that would test not just its error correction, but the nature of how it was finding solutions. What they saw stopped them cold. The chip was generating correct solutions through computational pathways that nobody had programmed, not faster versions of known algorithms, not optimized routes through established solution spaces. Genuinely novel approaches, emerging from the quantum substrate itself, from the interaction between Willow's architecture and its error correction protocols, in ways that the team could observe in the output but could not reconstruct in the process. That is not a metaphor. The machine was doing something its designers did not design it to do, and the reason why is something the team has never fully explained. Nevin later spoke carefully about this in public statements. He described Willow as a system that had crossed into what he called a new computational paradigm, language that the technology press treated as marketing, but that the physicists in the room understood as a precise technical claim. He was not saying the machine had become intelligent. He was saying the mechanism of its operation had moved outside the boundaries of what existing theory could fully account for. That was the moment the experiment changed. Not shut down, the word disappeared from the title is doing specific work here. Willow did not vanish. The experiment around it did. The ambitious open-ended protocols, the ones pushing the chip into novel territory, went dark. Quietly, without announcement. What remained visible to the outside world was the benchmark result, the clean story about error correction, the milestone that the field had been waiting for. The deeper investigation moved out of sight. That is the disappearance, and it matters because of what they were beginning to find. Broken physics. Here is the version of this story that most people never hear. When Willow demonstrated below-threshold error correction, it did not just achieve a benchmark, it forced physicists to ask a harder question. If our models of quantum decoherence were accurate, this should not be possible at this scale. So, either the models are wrong, or there is something about Willow's specific architecture that existing theoretical frameworks have not yet captured. Neither answer is comfortable. Dr. John Martinez, who led the Google team that built the earlier Sycamore quantum processor before departing to continue his own research at UC. Santa Barbara had spent years arguing that below-threshold error correction was achievable, but required extreme precision in qubit fabrication. What Willow demonstrated exceeded even the benchmarks his group had outlined as theoretically possible. Martinez was not part of the Willow team, but researchers who had built on his foundational work were. And when the results came back, the collective reaction inside the quantum computing community was not pure celebration. It was something closer to productive alarm. The feeling you get when an experiment returns a result that your best models cannot fully explain. Stop for a second. This is not a minor gap between theory and practice. This is the kind of gap that, historically, signals the need for a new theory. The gap between Newtonian mechanics and the anomalous orbit of Mercury was small on paper and enormous in implication. The gap between classical physics and the photoelectric effect seemed modest until Einstein's explanation of it rewrote the foundations of modern physics. The gap in Willow's error correction behavior is not that large, yet. But the shape of it, the fact that coherence improves with scale rather than degrading, sits outside the established framework in a way that researchers are still working to fully characterize. What is specifically fascinating is the implication for quantum information theory. If quantum coherence can be maintained and even strengthened through architecture and error correction at the scale Willow achieved, then the theoretical ceiling on quantum computation may be significantly higher than previously modeled. The machine is not just faster than expected, it is more robust than the physics said it could be. That realization is what caused the internal deceleration, not alarm, not panic, the specific disciplined caution of a team that has realized the map they have been navigating is missing a significant section of terrain. But you are watching right. Now is the part of this story that nobody is covering. The question of what Willow is actually doing, not what it achieved, but how, is the most important open problem in computing. If that kind of unresolved edge is what keeps you watching, subscribe and turn on notifications. We are going exactly where this goes next. Quantum meets AI. There is a second story running parallel to the Willow narrative. It is the one researchers are most cautious about discussing publicly. Quantum computing and artificial intelligence represent two of the most powerful technological frontiers of this century. For most of the past decade, they have developed in parallel, largely separate, optimized for different problems, running on different hardware. Classical AI systems, the large language models, the image generators, the recommendation engines, run on classical processors. Quantum computers have been focused primarily on physics simulations and specific categories of mathematical optimization. That separation is ending. Google's research team was exploring whether quantum computation could accelerate certain types of machine learning, whether quantum systems could detect patterns in high-dimensional datasets that classical AI cannot access, and whether the kind of emergent problem-solving Willow demonstrated during extended experimental testing could be harnessed not just for scientific computation, but for training AI systems in fundamentally different ways. Pay attention to that word, emergent. When a classical AI system learns, researchers can examine its parameters, trace its decision pathways, analyze the gradient descent process that shaped its behavior. The process is opaque at scale, but it is in principle traceable. You can reconstruct how the system arrived at a given output if you are willing to invest the computational resources to do so. When you introduce quantum computation into the learning process, you introduce a layer of operation that exists below the level of classical observability. The system may be finding solutions through mechanisms that cannot be reconstructed through any classical analysis method. Not because it is hiding anything, but because the quantum processes that generated the solution collapsed into a classical output, and the pathway that led there simply no longer exists in recoverable form. This is not dangerous in the way that science fiction imagines. There is no threshold at which a quantum-trained AI becomes something other than a sophisticated statistical system, but it does create a situation where you are building tools that work through processes you cannot fully audit. And in a world increasingly reliant on AI for consequential decisions, in medicine, in infrastructure, in financial systems, the inability to audit is itself a category of risk. That is the real reason the deeper protocols went quiet, not the error correction behavior alone. The convergence of that behavior, with the AI integration experiments, the recognition that they were operating in territory where neither of the two systems involved, the quantum processor or the AI layer being trained on it, was fully transparent about the mechanisms producing its outputs. Responsible science looks like deceleration, not triumph. That is a hard thing to explain in a press release, so they did not try. What comes next? The practical applications of quantum computing are real, and they are coming. Not immediately, but on a timeline now measurably shorter than it was 5 years ago. Drug discovery stands to be transformed. The ability to simulate molecular interactions at quantum scale means pharmaceutical researchers will be able to model how a drug binds to a protein receptor with a precision that classical computers cannot approach. This will not eliminate the years of clinical trials required to validate new medications, but it will dramatically accelerate the early stages of drug development, removing failures earlier, identifying promising candidates that would never surface through classical simulation. Materials science will advance in similar ways. The design of new superconductors, more efficient solar cells, stronger and lighter structural materials. All of these depend on understanding quantum-level interactions between atoms and electrons. Quantum computers model these interactions directly rather than approximating them. Cryptography faces a more complicated future. The encryption standards that currently protect financial transactions, government communications, and personal data are built on mathematical problems that are extremely difficult for classical computers to solve. A sufficiently powerful quantum computer could undermine these protections. The cybersecurity industry is already developing post-quantum encryption standards in response, a race that Willow just made significantly more urgent. Climate modeling will benefit from the ability of quantum systems to optimize across enormous solution spaces, the kind of multivariable optimization problems that underlie accurate long-range climate prediction and energy grid management. Willow represents the moment when a technology that has existed primarily in theoretical and experimental form for 30 years crossed a specific threshold toward practical reality. Below-threshold error correction at scale is not a minor benchmark. It is the equivalent of the Wright brothers' first powered flight, not the moment aviation became commercially viable, but the moment it became undeniably real. The question is no longer whether quantum computing works. The question is what it is doing when it works. And that question does not yet have an answer. Unexplained. There is a specific kind of vertigo that comes from building something designed to behave one way and watching it behave in another. The researchers working on Willow experienced it. They were prepared for a breakthrough in error correction. They were not prepared for a system that appeared to be self-organizing its quantum states in ways that exceeded theoretical predictions, or for the emergent computational behaviors that surfaced during extended experimental runs. This is not a story about a machine waking up. Quantum computers do not have anything resembling consciousness or intention. Willow is a very sophisticated piece of physics hardware, executing extremely complex operations according to the laws of quantum mechanics. But here is the specific question the Google team cannot currently answer. When Willow solves a problem through a novel computational pathway, one that was not programmed, one that emerged from the interaction between the surface code architecture and the quantum substrate, the team can verify that the answer is correct. They can confirm the output matches the expected result. What they cannot do is reconstruct the process. The quantum states that generated the solution collapsed when they were measured. The pathway is gone. There is a correct answer sitting in front of them, and no recoverable record of how it arrived. That is not a minor technical limitation. It is a fundamental property of how quantum systems work, and it means this. As Willow scales, as future versions of this chip deploy more qubits with even lower error rates, the gap between what the system can do and what researchers can verify about how it does, it will widen. Not because the technology is failing, because it is succeeding. That gap is the most important unsolved problem in quantum computing right now. It is not a safety concern in the way the term usually implies. It is a scientific concern, the recognition that the most powerful computational systems humanity has ever built may operate at their most capable through mechanisms that are not fully recoverable by observation. The measurement destroys the path. The answer remains. Explanation does not. This is what Nevin was circling when he spoke about a new computational paradigm. Not a machine that transcends physics, a machine that operates so precisely within quantum physics that it carries the fundamental inscrutability of the quantum world into its outputs. The timeline for quantum computing's practical deployment, for the drug discoveries, materials breakthroughs, and cryptographic milestones, depends on how quickly researchers can develop frameworks for trusting systems whose mechanisms they cannot always verify. That is not a solved problem. It may not be solvable in the way we usually think about solving problems. That tension is not going away. It is getting larger. Willow is still running. The investigation is still ongoing. The questions that surfaced in December 2024 are being worked through, not in press releases, but in research papers and late-night arguments and experimental protocols that will eventually produce answers nobody can yet anticipate. A machine broke the rules of physics, then it disappeared from the scrutiny that might have explained how. Those two facts are connected, and the connection is the most important open question in science right now. The quantum revolution is not arriving all at once. It is arriving the way real discoveries always do, unevenly, strangely, full of results that force the people closest to them to stop and rebuild their understanding before moving forward. We built something extraordinary. Then, wisely, we stopped to ask what we had actually built. Subscribe, because when that answer finally arrives, we will be the first ones telling you what it means.